So if you can see from unit 1, the total number of marks that will be appearing in your CBSE exam is 10. Out of the 10, 5 marks are from chapter 2, electrostatic potential and capacitance, right? So the demo that I'll
Yes,
be taking
sir.
is worth 5 marks. Got it? All right. So, yep. So do you have any idea of the topic?
Yes, sir. I have some.
Okay, so can you tell
There
me
is
how much do you know?
the derivations.
Okay, I'll ask you. I'll ask you. Okay. Do you, so what do you think electrostatic potential is?
Electrostatic potential, the amount of force required to move a charge from
Right.
one point to another.
It's from infinity to the point, right?
Yes, sir.
So a more refined way of saying is electrostatic potential at a point is the work done per unit positive charge in bringing a test charge from infinity to that point without any acceleration, right? So if you
Yes, sir.
let's suppose you have a unit charge, a unit positive charge, right? Right. So the amount of work done to bring this to a point of consideration, right? Without any acceleration, to bring it in a steady state without any acceleration from infinity to this point is called what? Electrostatic potential, right? So how would you represent this in a mathematical way? So it's given as V is equal to W by Q. So V is potential, right? Unit is voltage, or in short, volts, right? And W is the work done, right? And it's joules or J, right? This is V, right? And Q is the charge, and the unit of this charge is, what is the unit of the charge?
Coulomb.
Coulomb. Good. Coulomb, or capital C. Got it. So the unit of this together, right, which is 1 volt is equal to 1 joules by 1 coulomb. So this is the unit, which is volts, right? Volts is joules per coulomb, right? So this is the SI unit. You know what SI unit is, right?
Yes, sir.
So the unit is SI, which is volts, and it's a scalar quantity, which means which
There
means
is no
yeah,
direction.
there's no direction. There's only magnitude, right? So you
Yes,
cannot
sir.
have negative potential difference. It's always positive potential, right? So now going ahead, there's something
Yes,
called
sir.
potential due to point charge, right? So what do you think a point charge is?
So bringing one
No, no, no. I'm
point
asking what is point charge?
point charge. It's a point charge in a vacuum.
I'll tell you. A point charge is an idealized physical model. So let's consider this, right? This point, right? Consider this to be a point charge. So this is an idealized physical model, right? Which an let's say this is positive, right? This is the fundamental unit of charge, fundamental point, right? Let me like represent it in a better way. Let's consider this, right? This point charge is positive, and one point charge is uh, let's say this is positive and this is negative, right? So a point charge is an idealized physical model in which an electric charge is treated as if it were concentrated in a single infinitely small point, right? So a point charge is the smallest possible point in which an idealized charge is concentrated, right? So it's usually represented as a small circle within which houses a unit or a sign, positive or negative, and represented as like this, right? For positive, the arrow marks are outside, right? And for negative, the arrows are coming within, like this. Does it make sense, right?
Yes, sir.
Because when you have a positive point charge, the arrows of the electric field are always moving outwards, right? Like this. For negative, it is inwards, right? Okay. So there is one assumption, right? That this has no area, no volume, okay, and its physical dimensions are negligible, right? So there is no distance or diameter or anything. All physical, let's say, dimensions are negligible. Has no area, no volume. It's infinitesimally small point where the charge is concentrated, right? Okay. So if you have understood, you understood this part, no? You know what a point charge now
Yes,
is.
sir.
Now what we'll do is we'll
Yes, sir.
we'll find the potential due to a point charge. So when you have matter, matter has, let's say, atom is the fundamental particle, right? When you have a
Yes.
biological, let's say, entity, what is the fundamental unit? It's a cell, right?
Yes,
Beyond the
sir.
cell there is nothing which is living, smallest living particle, right? Beyond an atom there is no matter, right? So similarly, beyond a point charge, there is point charge is the smallest fundamental charge that could exist in the universe, right? Okay. So now we find out the potential due to the point charge, right? So consider one point charge. Let's say, let's say Q, right? I'll write Q here, right? So when you have a, like, this is a point charge Q, and you have to measure the potential at a distance r, right? Let's say this point, and the distance is r. Okay, so this is given by, mathematically, v is equal to 1 by 4 pi epsilon naught q by r, right? It's similar to f is equal to 1 by 4 pi epsilon naught q1 q2 by r square. It's similar to this. So it's very important to not be confused between the formula for potential and formula for electrostatic force. Okay? So just keep this in mind,
Yes,
because
sir.
it's fairly similar, right? So what do we understand from this formula? We understand that the potential is directly proportional to the charge and inversely proportional to the distance from the charge, from the point charge, right? So this formula can also be written as V is equal to K Q by R, where K is the constant, which is given by 1 by 4 pi epsilon naught, right? And the value of
Yes, sir.
epsilon naught, constant of permeability, is different.
It's 9,
Yeah, in air
9
it is 9.
into.
Yeah, 9 into 10, 10 power 9 Newton meter square per coulomb square, right?
Yes,
So,
sir.
value of K is 1 by 4 pi, which we know, epsilon naught, also given as 9 into 10 power 9 Newton meter square per coulomb square. This is in air, right?
Yes, sir.
So there are a few important observations that you have to keep in mind. Okay. Before I move ahead, do you have any doubts?
No, sir.
Fairly
Perfect.
easy, right? It's not very hard to understand.
No, sir.
Do you have any difficulty imagining stuff? Like, what is a
No,
point
I
charge?
can
You
easily
can imagine it
imagine.
inside your head, no? Like this is how a point charge is, because physics is all about imagination. You'll not understand unless you imagine stuff, right?
Yes, sir, I can.
Yeah, imagination is the key. Okay. All right. Now coming to important observations, right? Right. Important observations. When you have a positive charge, let's say positive charge, your potential is always greater than zero, right? For negative charge, your potential is always less than zero. And when the distance tends to infinity, right, your potential also tends to zero. Okay. So when the point charge is positive, the value of potential is greater than zero. When it is negative, it is less than zero. And when r tends to infinity, the value of potential tends to zero. So what do we conclude from here? We conclude that potential varies inversely with distance, as I mentioned earlier here, right?
Yes, sir.
Okay. So let me quickly go through what we did till now. We went through the definition for electrostatic potential, which means electrostatic potential at a point is the work done per unit positive charge. Very important, per unit positive charge in bringing a test charge from infinity to that point without any acceleration. Mathematically given by V is equal to W by Q. Let's see where. Yeah, here, right? Where V is the potential, W is the work done, Q is the charge, right? Okay. It is a scalar quantity. It has no direction, but only has a magnitude, right? And then we went through potential due to point charge. We learned what a point charge is, right? And then what is the potential due to that point charge, okay? Which is 1 by 4 pi epsilon naught capital Q by R, where this is the this is the constant K, and this is the value of point charge, right? And this is the distance from the point charge, okay? And we also went through the value, which is generally used in numericals, which is 9 into 10 power 9 Newton meter square per Coulomb square, okay? Then most important, um, these observations where V is greater than 0 when it's a positive charge, V is smaller than 0 when it's a negative charge, and R tends to infinity when V tends to 0, or V tends to 0 when R tends to infinity. And this concludes potential, or which is V, my bad, not P, right? V is inversely proportional to 1 by R. Okay. So moving ahead, there is something called potential due to system of charges, right? Until now we did potential due to a point charge, right? Now what we'll see? We'll see potential due to system of charges, right? So
Yes,
this
sir.
is called superposition principle. Are you aware of superposition principle or principle of superposition?
I think, yeah.
What do you think it is?
It's uh, a concept where there are like a system, isolated system where there's like two charges which influence each other.
Yeah, I mean partly correct, but it is more like it's a universal system, so it can be applied on electrostatics. It can be applied on anything, right? It's a principle. So we know that this potential due to system of charges follows this principle, right? So now what is
Yes,
this
sir.
principle of superposition? So if you have a linear system, you know what a linear system is, right?
Yes, sir. There is no dynamic change.
Yeah, so if
Be right.
one value changes, the total value changes linearly, right?
Yes, sir.
Let's say y is equal to 2x. So if x is 1, y is 2. If x is 2, y is 4. So it's a linear increase. It's not exponential, right? So in a linear system, the net response caused by two or more stimuli, right, is the sum of responses that would have been caused by each stimuli individually, right? It's more like, let's say you have q1, and then you have q2, then you have q3, right? These are individual charges, right, in a system, right? Right? And corresponding to q1, you have v1, you have v2, you have v3, right? So what is v1? V1 is, let's say, k q1 by r, assuming r is similar, or let's take r1, right? Now you have v2 is equal to k q2 by r2. v3 is k q3 by r3. Okay, all right. So together, right, if these three are in a system, one change in q1 can result in a change in v1, right? And in turn can trigger a change in the entire system linearly, right? So the
Yes,
total,
sir.
yeah, so the total stimuli experienced by a system due to two, uh, let's say, parameters is equal to the sum, algebraic sum of all of these. So for q1, q2, q3, and v1, v2, v3, total
So
v,
sigma of,
it's v1 plus v2 plus v3 basically. Sorry, right?
yes, sir.
Yeah. So it's more like total potential in a system is equal to algebraic sum of different potentials, right? And what is v1, v2, v3? It's nothing but 1 by 4 pi epsilon naught. So this is epsilon, you know this, no? This is not sigma.
Yes, sir.
Okay.
And I know it's yeah,
Oh, you said summation sigma.
yeah, yeah, yeah.
Yeah, okay, it's fine. Right. Right. So v is nothing but 1 by 4 pi epsilon naught, which is, let's say k only for simplicity, right? K is nothing but q1 by r1 plus q2 by r2 plus q3 by r3. Okay. So what does potential obey? Potential obeys the principle of superposition. Through that, using the principle of superposition, we can say v is equal to um, v1 plus v2 plus v3, and in turn we can say it's q1 by r1, q2 by r2 plus q3 by r3, right, into k, where k is 1 by 4 pi epsilon naught. Okay. Also potential is scalar, so simple algebraic addition happens. Simple algebraic, which is v1 plus v2 plus v3. There is no vector addition because it's a scalar quantity. You just add it, right? Was it clear? Were you able to understand?
Yes, sir.
Like, are you sure? Because a lot of kids find this
Yes.
part difficult to understand. So
So it's just a, near addition of all,
yeah, it is
all of
mere
it.
addition. But why is it mere addition? Because potential follows the principle of superposition.
Yeah.
Yeah,
Yeah.
you can't
So
just
it
you can't
increases
just tell
linear.
it's yeah, you can't just tell it's mere addition. You have to tell why is it mere addition, right? Because not in physics, in basically in science, if you're getting a piece of information, you have to make it clear from where you're getting the piece of information. So you might be aware when they're writing research papers, every paragraph will have an index saying that we got this information from another paper, and we got this information from another textbook, and so and so and so. You cannot leave any uh, gap. So similarly, in your answer sheets also, like keep it more presentable and say why. Why is very important rather than like mere assumptions, right? So why? Because potential follows the principle of superposition. What is the principle of superposition? One change in one quantity will result in a complete change, right? Due to this, you add it. And why mere addition? Because it's a scalar quantity and there is no vector addition, right?
One change in a one change in one quantity results in a change in every quantity.
Not every quantity, in the total quantity. So
Okay.
it's more like you have v is equal to v1 plus v2 plus v3. If the value of v1 changes, won't v change, right?
Yeah.
Yeah.
Yes,
Also,
sir.
there are different types of superpositions. You have wave superpositions. There is superposition in electrostatics and fields, which you are doing now. Then there is superposition in mechanical systems, in quantum mechanics, right? All these are like very complicated. But when it comes to electrostatics and fields, right, principle of superposition dictates that total electric field created by multiple charged particles at a given point is the vector sum of electric fields produced by each charge individually, right? So what is the total potential? V, right? What are the individual potentials? V1, V2, V3.
V1.
Yeah. So total, let's say total potential V is algebraic sum of each individual potential V1, V2, V3. So if V is dependent so much on V1, V2, V3, then a small change in V1 will result in total change of V, right? So let's say V1 is 2, V2 is 2, let's say V1 is 1, V2 is 2, and V3 is 3. Make V1 2, then the entire sum will change, right? So it's a vector sum as per the definition, but as potential here is scalar, so we just do,
Scalar.
yeah, we just do simple algebraic addition, V1, V2, V3.
The other one will be dynamic if it's vector, right?
Yeah,
Like if there's a vector unit.
right. So now moving ahead, we have one topic which is electric potential energy. Do you know what potential energy is?
Yes, it is electric potential, bringing one point from infinity to a field
The
to influence.
potential energy. It's more like potential energy is energy stored at rest, right? In simple
Okay.
terms, in when you were in high school, let's say
Cell.
in, yeah, seventh, eighth, ninth, you learned that if an object is at a distance, it carries some potential energy when it is at rest, stored energy. So as soon as it is released, the potential energy changes into kinetic energy and it moves,
Yes, sir.
right? So potential energy is energy possessed due to position. If it is here, then let's say if it is on my hand, potential energy is zero, right? When it is lifted, raised to a distance, at this position, potential energy has some value, right? So in other terms, potential energy is nothing but energy possessed due to position. So similarly, in this electric potential energy, the potential energy is the energy possessed due to position of the point charge, right? So let's say
Yes,
you
sir.
have 2 point charges. If they are at different positions, the potential energy changes, right? So
It's due to the this thing
position,
electric field of the charges, right?
yeah, yeah, basically, right? So let's say you have 2 point charges, right? Let's say this and this, right? 2 point charges with a distance r. Let's say this is q1, this is q2, right? So what is the potential energy? U. It's potential energy is U. You know that. Kinetic energy is Ke, right? So basically, U potential energy U is given by 1 by 4 pi epsilon naught Q1 Q2 by R, right? What do you think is potential energy in a mechanical sense? You know, it's potential energy U is given by mgh.